So with the previous discussion in mind, we're now going to define our abstraction. This abstraction is called a vector space over R, the real numbers. And now the definition is a vector space over R is a trio, so it's three things. We have a set called V, we have an operation of addition, and an operation of scalar multiplication. Scalars in particular being real. And this is what we mean by over R. Over R is an indication that the scalars are real scalars. Okay, so importantly, vector space is a trio. Vector space is not just this set. Right? A vector space is the trio of all three of these things together. That's a vector space. Okay, so anything, whatever this object might be, whatever this underlying set, we call it, might happen to be, whatever the elements in that set might happen to be, however I might happen to define an addition on those elements, however I might happen to define a scalar multiplication on those elements. This is called a vector space. With some additional requirements, we do have 8 properties that these operations have to satisfy. The addition has to be commutative. The addition has to be associative. There has to be a zero vector. You might call this an additive identity. There needs to be something that no matter what I add it to, I get exactly the same thing back. In other words, as far as addition goes, it's behaving kind of like the zero would. Furthermore, everything needs to have something called an additive inverse. That is, whatever vector you might be interested in this vector space, there has to be something I can add to it that we're going to call negative v that makes the sum equal to 0. Namely, now that 0 being this zero vector previously referred to. There needs to be a distributivity property. There needs to be what you might call scalar associativity. There's this other kind of distributivity. You might say here we're distributing the scalar, right? Whereas on the other hand here it's sort of like you're distributing the vector. Okay. And finally, we need for scalar multiplication to behave in a natural way. Multiplication by the real number 1 needs to give us back the same vector. Okay, so all of these 8 properties are things that you would call normal algebra. These are things that we would all sort of expect and hope would be true. So we're going to require them to be true for anything to which we give the name vector space, so that when we are doing are making arguments with vector spaces, our new abstractions, and anytime we're talking about vector spaces, we can do these kinds of things. Okay. So notice what we've got then is, going back to the notes from the previous lecture, we have arranged for an abstraction. We never specified what the objects are. These objects in this vector space, that abstraction that I've defined, could be anything. Right? We've simply talked about the properties that they must satisfy. We have to be able to do certain operations, and those operations have to behave in certain ways. And notice that the properties that we required, that we'd be able to add objects, that we'd be able to multiply objects by scalars, and that we'd be able to do standard algebra. Those are all here in our definition. We can add, we can scalar multiply, and we can do standard algebra. Okay, so this is our thing called a vector space over the reals. We've already made this note. Over the reals means that the scalars are real. For the moment, we're going to consider only real scalars. Later in the course, we will consider vector spaces that have different scalars. That will be significantly in the future, and we'll worry about that then. Okay, so first example of a vector space over the reals is Rn. If you consider the collection of vectors in Rn, that is indeed a vector space. Now, we have to check that this is the case. we have to go back up here to our requirements and ask, well, considering Rn, well, there is an operation of addition of vectors in Rn. There is an operation of scalar multiplication. You give me a vector in Rn and I can multiply by a real scalar. And furthermore, all 8 of these properties are satisfied. This is a true property of vectors in Rn, as is this one. There is indeed a 0 vector. Everything does indeed have an additive inverse, and etc. All these properties are satisfied. And you got to go through and confirm that these are easy confirmations. Okay. Now, here's a non-obvious example. That is what I'm going to call capital F on the interval from A to B. And this capital F is simply the collection of real valued functions defined on that interval on a real axis. So that's the set. That's the underlying set. Now, in order for this to be a potential vector space, in addition to an underlying set, I also have to have an addition operation and a scalar multiplication. So we're going to define those like so. What do I mean by adding 2 real valued functions? The operation I'm going to define here, what it means to add 2 real valued functions, is that the result is this function called f plus g. And now I'm going to tell you what this function is. This f plus g function, this brand new function. And I'm going to tell you what it is by telling you how to evaluate it. If you want to plug in some value x, the way you evaluate what the value of that function is by taking f of x and g of x. Keep in mind, these are real valued functions. That means that that's a real number and that's a real number. And this then is just good old, plain old addition of real numbers. So, using what we know about addition of real numbers, we can define this brand new operation here, vector addition. We call it vector addition because this is how we're adding what are indeed the vectors in this would be vector space. Okay. All right. Awkwardly, very often, we use the same symbol for the vector addition that we will and always have used for plain old addition of real numbers. So this can be a little bit confusing, and the student has to heads up on this. So whenever you see this symbol, you have to ask yourself, wait a second, what are the objects that are being added, and then interpret appropriately. So in this case, that plus, is that the old elementary school plus of real numbers, or is that a plus, the brand new, newly defined addition of functions? And well, you know it's an addition of functions because, well, I'm using it on functions. Okay. So this is how addition is defined, and our scalar product is going to be defined in a sort of a similar way. Specifically, if you want to multiply a scalar c times a function f, so this is our new scalar vector multiplication. The result is a function that I define by telling you how to compute it, and if you want to plug in x into this new function, here's the formula for how to do it. Notice, of course, that in telling you how to do that, I have to make use of real number multiplication. And you know that this is multiplication of real numbers because I'm multiplying a real number there times a, well, this is a real valued function, and so the value there is also a real number. So that is real times real. Okay. Okay. That's a lot of discussion just to tell you what this thing is. We have an underlying set of real functions, we have an addition operation, and we have this scalar vector multiplication. Now, is that a vector space? Well, in order to confirm that this is a vector space, set, operation of addition, operation of scalar multiplication. But then we have to go down here and confirm all 8 of these properties. And these are not so obvious. These are things where you have to actually go through and write them down. I'm going to show you how to check this first property, and the remaining will be exercises, things for you to check for yourself. Okay, so here's how we check the first property. The first property says I need to confirm that adding, if you switch the order that you're adding, that you get the same result. Okay, so said differently, I need to show that this function f plus g and this function g plus f are the same function. Okay. Now, how am I going to show that these are the same functions? Well, I'm going to show you they're the same functions by evaluating at the same input value and confirming that we do indeed get the same output value. So how do I know that these output values are always the same? Well, that's actually pretty easy, because that's a real number, that's a real number, and I know that addition of real numbers is commutative. Right? That's old news from elementary school. And therefore that's equal to this addition of real numbers. So what we have then is that these two functions, when you put the same thing into them, you always get the same thing out. And that means that these two are the same functions. And therefore this addition is commutative. This new addition of vectors is commutative. So that's how you prove property number 1. Good. We've now checked that property for this would-be vector space, and students can go through and do the remainder on their own. Okay. All right. So now let's go back to our theorem. We had this theorem from the earlier lecture. This theorem about linear combinations of of things, initially stated about vectors in Rn. And we found that this was an unfortunate choice of how to state this theorem, because it was too specific. We stated this specifically about vectors in Rn, and that's what got us into trouble, and we had to then redo it for functions. And then in any other future situation we find ourselves, we would again have to redo it. But so instead, what we're going to do now is take advantage of our abstraction. We have this abstract construction of a vector space, and now instead of Rn, instead of this specific vector space here, what I'm going to do now is state our theorem entirely in the abstract. Here it is. A linear combination of linear combinations of vectors in a vector space. Now this is again very ambiguous. I'm not saying which vector space. I'm not saying what the objects in our vector space are. I'm stating this about any vector space. Anything that satisfies the properties that we enumerated previously. And my assertion is that a linear combination of linear combinations of those vectors is, as required, a linear combination of those vectors. So we're going to state and prove this in the vector space and be done with it completely. So here we go. Our vectors in a vector space. Here we'll look at linear combinations of those vectors in that vector space. We consider now what would happen if I took a linear combination of those linear combinations, right? And that I can expand out to this, and I can use, now wait a second, am I sure that I'm allowed to do the following? Am I allowed to multiply this in there and rewrite that scalar as that? Yes, that's one of our properties of vector spaces. I'm allowed to do that particular algebraic move, and other details analogously. And my result is, you see here, a linear combination of my original list of vectors in that vector space as required. Okay, so here's the wonderful thing. having stated and proved this theorem in the abstract about a vector space V, this now applies to all vector spaces. So, in fact, if I had just done this in the first place, if I had never gotten around to proving that theorem for Rn or proving it for functions, if I had just stated and proved this theorem in the abstract in the first place, I never would have had to prove this. Never would have had to do that at all. This is an immediate consequence of the theorem we just proved. Never would have had to state and prove this theorem. It's an immediate consequence of what we just proved, etc. Okay. And furthermore, this would apply, this theorem that we just stated and proved, will apply to any future vector space we might encounter. Vector spaces we haven't even thought of yet. This theorem applies to those vector spaces. So, for example, here's one. Let's consider the collection of all 3x5 matrices, where we have the usual addition of matrices and the usual scalar multiplication of matrices. Well, we have a set, we have an addition, we have a scalar multiplication. You can go through and confirm that those 8 properties, the requirements, are satisfied. That's just a matter of going through and confirming that matrix algebra does indeed behave the way that we listed. It has that natural algebra that we, the properties of which we enumerated in our definition of a vector space. And having observed that, not only do we know that this is a vector space, but that means that we know that this theorem applies to that new vector space. I don't have to state this and prove it again. I've already proved it in the abstract, therefore I don't ever again have to prove it in the specific. Okay. So what we do very often in linear algebra is we state and prove theorems in the abstract, so that we only have to do it once, so that we don't have to do it over and over again. And furthermore, once you understand that a object, say this, once you understand that it's a vector space, as soon as you show that it's a vector space, because you've been proving theorems in the abstract, you get for free immediately, as soon as you show that it's a vector space, then you get an enormously long list of theorems about your new object that are automatically true for free because you proved them in the abstract about vector spaces.